Okay, so welcome to this video. Now, in this video, we want to look at this partial differential equation here, and we're given a few ideas about how we might try and solve this problem. Alright, so there's a very interesting description of the problem here in what's known as the wave equation, but let's not worry too much about that right now. Let's just try and jump into the problem and do the calculations. So the first part of the problem, part A, it asks us to consider a very special form of this function u. So u here is a function of x and t, so position and time. And we want to look for a solution which is of the following form. It's a function of this very special combination x plus lambda t. Now, I find this combination a little bit confusing, so what I'm going to do is I'm going to start by giving this a name. So I'm going to start by saying, let's let our variable, which I'm going to call eta, this is a Greek letter eta, I'm going to let that be x plus lambda t. So this really just makes it a bit easier for me. I have one variable, g is a function of one variable, and here is that one variable. So we have u, which is a function of x and t, is a function of g, which is a function of eta, which is a function of x and t. Now, a very common way to write this out is that u, which in this case is really the same as g, is a function of eta, and eta depends on x and t. So this dependency diagram is quite useful whenever we're trying to do partial derivatives, because it tells us how to apply the chain rule. So let's answer the first question. Alright, so what's the first question really asking us to do? It just says calculate u subscript xx and u subscript t. Now, those are really just partial derivatives. They're really convenient ways to write down the partial derivatives, where u subscript xx is the second partial derivative with respect to x, and u subscript tt is the second partial derivative with respect to t. So we're really just being asked to calculate two second order partial derivatives. Okay, so how do we do that? Well, I'm going to have to start by calculating the first order derivatives. So what is u subscript x, which is just the partial derivative of u with respect to x? That is the partial derivative of g of what I've called eta. Now, the chain rule just tells you that this is going to be the partial derivative of g with respect to its variable, eta, times by the partial derivative of eta with respect to x. Now, in terms of our chain diagram, this is the partial derivative of g with respect to eta, and the partial derivative of eta with respect to x. So these two parts of the chain diagram. So, well, partial derivative of g with respect to eta, I'm just going to leave that as it is for now. Instead, let's look at the partial derivative of eta, which was x plus lambda t. So I want to take the partial derivative of this with respect to x. Now remember, t, when we take a partial derivative with respect to x, t is being held constant. So this doesn't affect the partial derivative. And this is a constant. Its lambda was a constant in the problem. So as far as x is concerned, these two terms here, these are both constant. So the only thing that really matters is the x, and when you take the derivative, that's going to be the partial derivative of g with respect to eta times, well, partial derivative of x with respect to x is 1. And if I'm multiplying by 1, I usually don't write that down, so it's just 1. And the partial derivative of g with respect to eta, that's really just saying the partial derivative of g with respect to its argument, which is to say it's the derivative of this function g. So this is the answer. U of x is really just the derivative of g with respect to its argument. All right, so let's try and now do the second derivative with respect to x. So u x x. Well, that's really just going to be the partial derivative with respect to x of the partial derivative of u with respect to x. That's literally what it means. Now, we've already worked out this term here. It's this thing here. So it's going to be the partial derivative with respect to x of this expression here. So this is the exact same situation we were in before. I have this thing g prime, the derivative of g. It's really just a function of my new variable eta, and that also just depends on x and t. So when I want to find the partial derivative with respect to x, there's really just two parts of the diagram I need to look at. I need to look at the partial derivative with respect to eta of this g prime, this derivative of g, and the partial derivative of eta with respect to x. So this is going to be the partial derivative, by the chain rule, the partial derivative of g with respect to eta times by the partial derivative of eta with respect to x. And we already worked out the partial derivative of eta with respect to x. It was this combination here, which is really just a 1. So that is going to be the partial derivative. Well, it's just going to be the partial derivative of this with respect to eta, which is going to be the second derivative of g at eta. And I can really just write this as the second derivative of g at my variable x plus lambda t. All right, so we've answered half of the first problem. That's the second derivative of u with respect to x. It's given by this very nice formula here. And the calculations for UTT are very similar. So let's repeat what we did, but with t instead of x. So I want the partial derivative of u with respect to t. It's just going to be, well, it's going to be the partial derivative of g with respect to eta times the partial derivative of eta with respect to t. So if we go back to my dependency diagram, we can see how this works. So it's the same as before. We're still going to look at this chain here. So we're still looking at the derivative of g with respect to eta, but now instead of looking at the x dependency, we're looking at the t dependency. So it's a partial derivative of eta with respect to t. It's the partial derivative of g with respect to eta times the partial derivative of eta, which is just x plus lambda t, over the partial derivative of that. Sorry, it's just the partial derivative of that with respect to t. Now, as before, this first one, g is just a function of eta, so the derivative of that is just eta. And if you want to look at the partial derivative of x plus lambda t, And the partial derivative of this other term, well, again, x doesn't depend on t, and lambda is a constant. So when we're taking the derivative, the only thing we really need to focus on is this t, and the derivative of this with respect to t is just lambda. So that's a little bit different from before. So here we actually have lambda times the partial derivative of g with respect to eta. And now what about the second derivative? Well, we're going to do the same thing. To find the second derivative with respect to t, I'm going to just find the partial derivative with respect to t of the partial derivative with respect to t. Now we've already worked this out. It's this expression here. So I'm trying to find the partial derivative with respect to t of lambda times the derivative of g evaluated at eta. So this is the same thing we had before. So we keep seeing this same pattern again and again. I have lambda times g prime, that is a function of eta, which is a function of x and t. So when I do the chain rule, I'll get a contribution from this chain here and a contribution from this chain here. So this is going to be the partial derivative with respect to eta of lambda times g prime, and I'll say of eta, times the partial derivative of eta with respect to t. Now, this is just an expression of eta, so when I do the partial derivative, I just get a lambda times the second derivative of g. And this second term, again, it's just the partial derivative of x plus lambda t with respect to t. And again, that's just going to be lambda. So we get lambda times lambda, or lambda squared, g second derivative of eta. So let me just summarize what we found. We found that u x x is really just the second derivative of our function g evaluated at x plus lambda t. And we found that our second derivative with respect to t is really just lambda squared times the second derivative of g. Alright, so that's part A. And it really is just a lot of calculations, making sure you can actually find these partial derivatives. What's interesting is what we're about to do in part B. So we're going to take these expressions, and we're actually going to work out how we can use this to find a solution to that wave equation. Alright, so I think this next part is actually the fun part of the exercise. We're going to take our two partial derivatives. So these are the partial derivatives of this expression here, and we're going to use it to actually find something that solves this differential equation. And it's going to be quite a general solution. So what can we do? Well, this is our differential equation. So let's just take these and plug these in here. So substituting the result from part A into the differential equation just gives, it's going to be UTT minus 16 UXX. Well, UTT is apparently lambda squared times the second derivative of our function g at x plus lambda t minus 16 times, well, minus 16 times the second derivative of our function g at x plus lambda t. Now that's very nice because you can see there is a common factor here. You can see there is a lambda squared minus 16 all multiplied by the second derivative of g evaluated at x plus lambda t. Now if you look back at the original equation, it says we want that to be 0. meaning all of this has to equal 0. Now there are really two choices here. There is the choice to look for functions where the second derivative is always 0, but that's not very useful. It does solve the problem, but not in a very useful way. So instead, what we're going to do is look for things where this term is 0. Make sure that this is always 0. So we will always have a solution if lambda squared minus 16 is equal to 0. And this is equivalent to saying that lambda squared is equal to 16. Now, we know how to solve quadratics, but this is a particularly easy quadratic to solve. You're just going to get lambda is equal to 4 or lambda is equal to minus 4. So we found two possible solutions. We found ones where lambda is equal to 4 and ones where lambda is equal to minus 4. Okay, so I'd like to leave you with two challenge problems. So I'd like to ask you, what does this solution look like? So we know, based on what we've done, these both are going to solve that wave equation. They're both defined in terms of differentiable functions. They're twice differentiable. In fact, they're infinitely differentiable. And this is x plus lambda t, where lambda is either plus or minus 4. So what do these look like? Now the question's a bit vague, and I'm intentionally leaving it a bit vague so you have to think. But one way I would try and get a bit of an idea of what these look like is by trying to make a plot. And I'm not going to try and make a plot of x versus... now I'm not going to try and make a plot of u versus x or u versus t. I'm actually going to make a plot of u versus that eta variable, because we're really just trying to plot u is equal to the sine of eta. This one variable, it's a complicated expression of x and t, but it is just one variable. And we can plot sines. We know how to plot sines. It looks like this. So we know interesting things happen, for example, when eta is equal to pi over 2, and when eta is equal to pi, or when eta is equal to 3 pi over 2. Now, one way to try and get a handle on what this looks like is, let's try and concentrate on those interesting values of eta. So for example, this value here, we know this is the top of a wave, and we want to see where that moves. So I'm going to ask the question, what happens to x if t increases, and we're looking at the very special point where eta is equal to pi over 2. So I will give you a hint. Write x as an expression in terms of eta and t. So when you do that, one question you can ask yourself is, which direction does... So when you do this, ask yourself the question, which direction does the wave move? So really I'm asking, if t is changing, how is x changing? And you can do this if you're able to write x as an expression in terms of eta and t. Okay, so thank you for watching the video and good luck with your mathematical studies.